Hello and welcome. I'm Alexis Carrera, a PhD student in the Department of Agronomy at Kansas State University and part of the SWCS KSU student chapter. Today, I'm going to be talking about erosion mechanisms and some methods used to mitigate excessive soil loss in agricultural systems. Erosion is defined as the removal and transportation of materials via geophysical forces. We'll be focusing specifically on wind and water and how these forces can remove productive topsoil and expose nutrient-deficient subsoils. As a preface, erosion is often perceived as a bad thing. As conservationists, we are understandably concerned with the consequences of excessive soil loss, mostly due to anthropogenic activity. However, it's important to remember that erosion is totally natural. These amazing forces have been shaping landscapes since the beginning of time. Think about how wind-blown sediments have formed the Vermilion Cliffs, or how the Colorado River has been cutting through the Grand Canyon for millions of years. These geological masterpieces are the result of physical weathering. Physical erosion takes place in 3 steps: detachment, transportation, and deposition. The initial force detaches the particles from their original source. They are then transported via wind or water, and the particles are then deposited in their new place. Wind moves sediment particles via creep, saltation, and suspension. Stronger winds can move larger particles via this creep mechanism. The force of the wind pushes the particles, rolling them along the landscape, sort of like a ball. Smaller particles are pushed by winds and bounce off the landscape via saltation. The particles can also break into even smaller pieces when they bounce off the ground. Suspension is probably what most of us think when we imagine wind transporting sediment. Particles are suspended in the air and are blown towards their destination. Dust storms are extreme examples of suspension. This first image here was taken during the Dust Bowl back in the 1930s. And although conservation efforts have been made since the Dust Bowl, dangerous dust storms continue to be a concern in parts of Kansas. This photo here in the bottom left was just taken in 2021. Moving on to water erosion, the force of raindrops are more important than the movement of running water. Upon impact of individual raindrops, particles can be detached from their original source. Larger raindrops fall with more force and energy, impacting the soil more than smaller raindrops. Moving water then transports these sediments and ultimately deposits them to a new location. Flow of water and sediments following precipitation events leads to rill erosion. In this first image, we can see an example of this naturally occurring in the Flint Hills in Kansas. Shallow rills can be evened out using tillage, but the sediment is already lost and the damage has been done. Eventually, the rills here form gullies, which can be seen here not too far from where the first photo was taken. These gullies appear as huge cuts in the landscape. These examples are naturally occurring, but it is well known that anthropogenic activity such as tillage can lead to increased erosion and the formation of rills and gullies on ag land. Farmers, conservationists, and researchers today continue to investigate how we can preserve our cropland soils while maintaining productivity. Farmers are adopting reduced tillage practices as one way to protect their soils. Approximately 21% of cropland in the U.S. is no-till, which is currently defined as leaving a minimum of 30% of crop residue on the soil surface. The photo on the right is an example of conservation tillage. The land was tilled, but sufficient residue was left on the surface. Some no-till operations introduce an additional soil health practice, planting cover crops. Cover crops are planted between cash crop seasons and may offer an array of benefits for the soil. From a basic erosion standpoint, cover crops provide a physical mat of protection from the erosive forces of raindrops. Additionally, the living roots of cover crops also help keep the soil in place. Here's a more stark visual comparison. Which soil looks better protected? The soil on the left is much better protected from rain and wind, with both the cover crop and the residue left from the previous crop protecting the soil underneath, while the tilled soil on the right is much more vulnerable and susceptible to loss. Additionally, we can see the benefits of cover cropping from an erosion standpoint in this graph courtesy of my fellow K-State graduate student Tamjid Sakib. Watershed studies conducted by K-State provide evidence for great reduction in sediment loss just by the presence of a cover crop. Even in no-till systems, such as the one in this study, more sediment is lost when there are no living roots present. There's even a visual difference in the runoff water from both treatments. On the left, we see a lot of sediment coming off of the bare plot, and less sediment flowing from the plot with a cover crop present. Closing, erosion is a totally natural process that has shaped the landscapes people travel tremendous ways to see. I hope you leave with new knowledge and perspective on the geophysical forces that build the world around us. Look out for part 2 on erosion, where my colleague will be diving deeper into the benefits of cover crops for preventing erosion and promoting soil health.